Okay. Yeah. So good morning, students. Am I audible to you? And can you see the screen? Good morning, all of you. Am I audible to you? Okay. Please respond. Am I audible to you or not? Is the audio clear? Yes. Okay. So we'll continue. See here. So if you quickly recall that we learned in the first lecture of this thermodynamic relations, I told you if Z is any property that's depending upon two variables, then we know this is the differentiation total derivative of this. And if Z is Z of x comma y, we got the cyclic relation dou Z by dou x at y into dou x by dou y at z into dou y by dou z at x is equal to -1. We got this particular value when this Z is depending on this x and y. Next, so we from the things that we have, we derived something called Maxwell relations from first TDS equation. The first Maxwell equation that we got is minus dou p by dou s at constant v is equal to dou t by dou v at constant s. And second Maxwell equation that we got is dou t by dou p at v is equal to dou v by dou s at p. And also, if you see here, dou v by dou p at constant pressure is equal to minus dou s by dou p at t, and dou p by dou t at v is equal to dou s by dou v at t. So we have four Maxwell relations that were established based on the first, second TDS equations, and by finally Gibbs using Gibbs function and Helmholtz functions. Next, we have summarized all the four Maxwell relations, and then we thought of finding the variation in change of internal energy. We then thought of finding the change in internal energy by assuming if U is a function of temperature and volume, then we deduce some common relationship between the change in internal energy and this temperature and volume. At times, this board is hanging, actually that's the issue. Just a second, let it work. Okay. This is a bit less responsive today, so that's the issue. Okay, so see here. So finally we deduce some expression finally for changes in du in terms of temperature and volume, and this is the final expression that we got out, that du is equal to T into dou s by dou t at v dt plus T into dou s by dou v at dt minus p. And after applying this dou s by dou v at t as dou p by dou t at v using Maxwell equation, we found out different terms, and we have finally summarized that change in internal energy for any gas is equal to du is equal to cv dt plus T into dou p by dou t at v minus p dv. And then I asked you to try for this. So how many of you tried this expression? dH is equal to cp dt plus v minus T into dou v by dou t at p. How many of you tried this? Please tell me honestly. I asked you to try this. Correct? I derived this and I asked you to try this by assuming H is a function of temperature and pressure, and also taking entropy as function of temperature and pressure, and to achieve this equation. Did any of you do this? No? Yes or no? You didn't do this? Okay. So you didn't find some time to try this. So please try. See, there is nothing difficult here. See, I assumed here initially this internal energy is a function of temperature and volume. So you assume that this internal energy is a function of, enthalpy is a function of H is equal to H of T comma P. Then write this equation, dH is equal to dou H by dou T at P into dt plus dou H by dou P at T into dP. Assume S is also a function of temperature and pressure, and then derive this. Again, in second TDS equation, TDS is equal to dH minus VdP. In place of ds, substitute this value and you can derive. And you can use one Maxwell equation, suitable equation, to deduce this. Then we got definitions of volumetric expansivity and isothermal compressibility here. And then I told you this Mayer's equation, and if time permits, I told you that I'll derive you this in tomorrow's class after completing all gate questions. If we have some time left, then definitely I'll derive you that. Okay, Cp minus Cv is equal to Tv beta square by Kt. And of course, for ideal gas, we calculated what is beta. Volumetric expansivity of an ideal gas is nothing but 1 by absolute temperature. So this beta is inverse of this temperature, absolute temperature, and this isothermal compressibility Kt in case of ideal gas. If you see this derivations and all, we got 1 by P for ideal gas. So volumetric expansivity is equal to inverse of the temperature, of course absolute temperature, and this isothermal compressibility is again inverse of absolute pressure for an ideal gas. Correct? And I have shown you why Cp minus Cv is equal to gas constant R in this case. So as per Mayer's equation we have this. So for ideal gas, if you put beta is equal to 1 by T and Kt is equal to 1 by P, then Cp minus Cv, by substituting this beta and Kt here, after final analysis we got here R. So Cp minus Cv is equal to R for ideal gas. This is what I told you, correct? So this is the point where we stop. So now we'll extend our discussions. Application of Maxwell equations in two-phase systems. Maxwell equations. Let me write this combinedly. Applications of Maxwell equations in two-phase systems. So basically, when there is a system which is under phase change, then for example, if a liquid is getting vaporized, there will be some phase change process for this, which is called vaporization, and we have different terms there, correct? So if application of Maxwell equation in two-phase system, so if you apply this Maxwell equations, let us see what happens. Okay, so let us suppose there is a system for which we have two different pressures. Something like this. Okay, this is P1, this is P2. P1 saturation pressure, of course, here. This is P2 saturation, and these are the temperatures corresponding to T2 saturation and T1 saturation. Okay. So now if you look at Maxwell equations, let us apply one Maxwell equation here. See, this is temperatures and pressures which are at saturation conditions. So inside this dome, the content is in wet vapor, in wet vapor phase. So if you apply this, this equations, if you apply this, just a second, students. This again got stuck. Okay, fine. So if you see here, this is the Maxwell, these are the four Maxwell equations. So let us consider this Maxwell equations, because phase change and all, they occur at a constant temperature. So and also volume increases. So let us consider this last Maxwell relation, which is dou P by dou T at V is equal to dou S by dou V at T. So if you apply this, dou P Pt SV, correct? Okay, so see here, we have dou P by dou T is equal to dou S divided by dou V at constant volume, and this is at constant temperature. What about this V? Okay, so this is what the Maxwell equation we have, correct? This board is troubling me like anything. See here, dou V at T, and this is Maxwell relation. Correct? Since during phase change we have this temperature as fixed, so we can write at saturations dP by dt at saturation stage is equal to ds divided by dV at saturation stage. So if you write this, because at saturation stages these temperatures are constant on the right hand side, and here pressures and temperatures, they generally remain the constant, so we can take ordinary differentiations. Now, so this implies dP by dt at saturation temperatures, at saturation conditions is equal to, or else we can write into dV at saturation states is equal to ds. Correct? This is what we can write. Now, at saturation conditions, to calculate this ds, we have Tds is equal to dH minus VdP. So if you apply this process for a constant, this thing for a single process at a time, then this dP is 0, because during phase change P is equal to constant. All these ratios are at two states, means if you take this as 0.1 and if you take this as 0.2, we are applying this at two states. But if you want that entropy difference at a single point, if during phase change, Pressure remains constant, so dP is equal to 0. This is what we can write. So this implies ds is equal to dH divided by T, and for any condition during the phase change, if this is HF corresponding and if this is Hg corresponding values, then this dH by T is nothing but HFG divided by T of saturation, which is Hg minus HF divided by T saturation. This is entropy change, correct? Because we know ds is equal to dH by T, and dH is nothing but the change in enthalpies, so HFG divided by T saturation. So let us put it here. So dP divided by dt at saturation conditions is equal to, or else you can write maybe into Vg minus Vf at a particular saturation state is equal to ds at a particular saturation state, which is Hg minus Hf divided by T saturation. Hg minus Hf divided by T saturation. So if you are discussing at two different pressures, then definitely they have two different saturation temperatures, like we have done in that case. If you are talking about two different pressures simultaneously, then there are two different temperatures that are saturation to them. So dP by dt saturations is equal to HFG divided by T saturation into VFG, which is Vg minus Vf. And this equation is called Clapeyron equation. Clapeyron equation, and by using which you can find the value of this latent heat actually. So HFG is equal to dP by dt at saturation, and this. Now if you write this result in an elaborated way, you can have for these two states, if I am applying P saturation at state 2 minus P saturation 1, means these are the 1 2's corresponding. P saturation pressure at this P2. Okay, let us write this 1 2 because we have named them as P1 and P2. So let us suppose this is state 1, state 2. So saturation pressure at P2 minus saturation pressure at P1 divided by saturation temperature at state 2 minus saturation temperature at state 1 is equal to HFG. Now at what temperature you will take HFG? The temperature at which you will take this HFG is average temperature of these two. Okay, so because HFG is different for these two, and we can take this HFG at some mean temperature corresponding to these two. So the property is here. So HFG will take at a temperature which is the average of these two. Similarly, the property T saturation also will assume the T sat as average of T sat 1 and T sat 2 into Vg minus Vf. This is what we have for Clapeyron equation. And since if you know the saturation pressures and saturation temperatures, you can calculate HFG at some mean temperature between these two just by interpolating the things. Okay, clear? Did you all understand how did we got this Clapeyron equation? Because see, this dP by dt at constant volumes or at saturation conditions, basically at these two conditions, is given by this equation. Okay, so this is called Clapeyron equation, with which you will generally find this HFG, latent heat of vaporization. Okay, clear? Fine. So I'm going for the next step. So now if you write Clapeyron equation, we got at two different saturation pressures and temperatures. This is equal to HFG at the intermediate temperature divided by T saturation into Vg minus Vf. Correct? Now in this equation, if you make two assumptions, assume the first assumption we can make is, normally if you see T, for example, if this is V and something like this, then if this is the state, Normally, if you compare this Vf and specific volumes, of course, so Vf and Vg, this Vg is very far when compared to Vf. So Vg will be generally very much high when compared to Vf. And because practically these fluids are occupying a confined volume because atoms are closely placed and all. So practically speaking, this Vg at any given pressure P is equal to constant. For example, P1 is equal to constant. This Vg will be greater than Vf. So which means what can I write? Vg minus Vf is almost equal to Vg. Correct? Because this difference, this Vf which is very small when compared to Vg, then this difference is almost equal to Vc. Correct? If this is very small, which means this is tending to 0. So Vg minus 0 will tend to Vg again. So if you see, if you make this assumption, assume Vg is very much greater than Vf. And second thing, normally for vapors, we can't apply ideal gas equations. Correct? I told you this. But now if we assume for analysis purpose that vapor is behaving like an ideal gas, assuming vapor to be ideal gas. Actually, it is not. So that's why we are assuming. Okay. Assuming vapor to behave as an ideal gas. Assuming a vapor to behave as an ideal gas. So if you assume this vapor to behave as an ideal gas, and if I assume this Vg is very much greater than Vf, now what can I do? We can write dP by dt at saturation states, at two different saturation states, is equal to HFZ divided by T saturation into this Vg minus Vf. If you are neglecting this Vf, we can write it as Vg. Correct? And if you are applying ideal gas equation, P sat into Vg is equal to R into T sat. Correct? If you apply this ideal gas equation at this state, PV is equal to R T sat. So this implies Vg is equal to R into T sat divided by P sat. Correct? Saturation temperature divided by saturation pressure. So if you are assuming these two, that this vapor is also behaving as an ideal gas, but actually we can't. But to derive some equations and all, we are assuming that. So if you put this Vg is equal to this in this particular step, dP by dt saturation is equal to HFZ divided by T saturation square, because this T saturation into, when you multiply this, we'll be getting one more T saturation into R into P saturation. This is the equation that is with us. Correct? If you substitute this Vg as R into T saturation temperature divided by saturation pressure, then this is the equation that we have. Okay, so now if this is the equation that we have, let us write this once more. dP by dt saturation is equal to HFZ into P saturation divided by T saturation square into R, characteristic gas constant, which is universal gas constant divided by molecular weight. So generally if you are dealing with steam and all, Ru divided by 18, because molecular weight of water is 18. So this is the way. So now if you make small adjustments, we have 1 by P saturation into dP is equal to HFZ divided by R. Once if substance is fixed, these two are fixed. So HFZ and R into dt, T saturation square, we have dt, correct? 1 by T saturation square into dt. This is what we have. So now if you integrate it between two conditions, P saturation 1 to P saturation 2, T saturation 1 to T saturation 2. If you integrate this, because TV this is P1 is equal to constant, and this is P2, which is of course greater than P1. So now if you see, if you want to identify this change between two saturation pressures, this is P1 sat and this is P saturation 2, and this is corresponding T saturation 1 and this is corresponding T saturation 2, because this saturation temperature is a function of saturation pressure. So if you apply this between these two states, if you apply, then what happens? Integration of 1 by p sat is how much? Log p sat. Correct? So ln 1 by p sat 1 minus 1 by 1 by p sat 2 minus 1 by p sat 1 is equal to this HFZ. If you take this as constant, we have, correct, HFZ into 1 by T saturation square is minus 1 by T, so minus of 1 by T saturation 2 minus 1 by T saturation 1 between these two states. So now if you apply this 1 by P sat into dP is log P, and log of this value minus this, sorry, this is ln P sat 2 divided by P sat 1. Okay, because we need to apply log for the limits individually. So integral 1 by x dx is log x. So log P sat 2 minus log P sat 1, which is this expression. So if you remove this minus sign here, we have ln of P saturation 2 divided by P saturation 1 is equal to HFZ divided by R into 1 by T saturation 1 minus 1 by T saturation 2. So means if you know this value of HFG at some intermediate temperature, which is the average of these two, and if P saturation 1, P saturation 2 are known to you, then if you know T saturation 1, you can find T saturation 2. Means basically using this relation, which is called Clausius-Clapeyron relation. Clausius-Clapeyron relation. Using this relation, you can find what is the corresponding saturation temperature with respect to a saturation pressure, if you know other things. Okay, so this is how you can identify what are the saturation temperatures at different pressures, and also this latent heat of vaporization, basically, if all these four quantities are given. Clear to all of you? And this equation is called Clausius-Clapeyron equation, which we assume this vapor here at this states is behaving like a ideal gas, which is actually not in practice. Okay, clear to all of you? This is just deduction from this Clapeyron equation. In Clapeyron equation, we have this: if the dP is the difference between P2 and P1, and if dt is the difference between T saturation and T saturation 1, then from the application of that Maxwell relation, we got this particular equation where these properties corresponds to the temperature, which is the mean of these two temperatures, means somewhere here. Okay, this HFZ and VG and VF here. Okay, with respect to white lines. Clear to all of you? Did you all understand this Clausius-Clapeyron equation? This is purely mathematical, nothing, Yeah, we use these equations to identify latent heat of vaporizations. Means out of these quantities, if something is known and if one quantity is not known to us, we can evaluate. For example, if I give you this as some 30 kPa, 100 kPa, and at 100 kPa, this is 100. And latent heat of water is around 2257 and all. I mean, steam latent heat of vaporization is 2257 and all. So then you can calculate what is the saturation temperature corresponding to 30 kilopascals. Okay. So this is how you can utilize these equations and you can find the values. Of course, the actual values will change because our assumption that vapor behaving as an ideal gas is not very realistic in actual cases. Okay. Clear to all of you? So can I go for the next part? Okay. So now we'll identify something called Joule-Thomson coefficient. Joule-Thomson coefficient. Okay, so now we'll see what is this Joule-Thomson coefficient. Normally, during throttling, this value dou T by dou P, throttling in small device is isenthalpic, of course. So dou T by dou P, this value is really important. Means If pressure is dropping, this value tells us at constant enthalpy whether temperature will drop or temperature will increase, correct, at constant H. So during throttling, this value is really important to us because at constant enthalpy, if delta P is, if this complete value is positive, then for a positive change in pressure, this temperature increases. I mean, temperature change is also positive. But if this is less than 0, then we can decide, means basically when you are changing pressure of a fluid, what happens to the temperature of the fluid? That's what we come to know using this Joule-Thomson coefficient, and this ratio is the Joule-Thomson coefficient for any substance. Means when a substance or when a fluid is undergoing an isenthalpic process, what's the relation between its change in temperature and change in pressure? Is it positive or negative? And this value is important to us. Why we'll learn within coming to time. So see here, during throttling of a fluid, the temperature and pressure of a fluid may vary depending upon the throttling process. The change in temperature and volume, I mean pressure, the change in temperature and pressure, the change in temperature and pressure of a fluid during throttling is given by Joule-Thomson coefficient. Mu, and this mu is equal to dou T by dou P at constant enthalpy. Okay, so now this mu tells us what happens to the fluid during a isenthalpic process. If mu is greater than 0, means dou T by dou P at constant enthalpy is greater than 0. And you know, generally in throttling, we assume some pressure drop of the fluid because there will be some okay. So during throttling, we generally experience the loss in pressure of the fluid because pressure energy which is initially in the fluid gets converted to some other form, maybe like heat dissipations and all these things. So if you see, if mu is greater than 0, dou T by dou P of H is greater than 0. This means we can write dou T should be less than 0, which means temperature decreases. Correct? Because in throttling there is pressure drop. If pressure is dropping, then the change in pressure is negative because del P is always final minus initial. So if pressure is dropping in throttling, P2 minus P1 will be negative. But since to maintain the positive ratio of these two, this del T has to be negative, which means temperature decreases. Actually means for a fluid with mu greater than 0, if you throttle the fluid, then the temperature of the fluid decreases. Next, if mu is less than 0, dou T by dou P at H is less than 0 and dou T is greater than 0, because you know during throttling there is loss in pressure, so del P is negative. So since del P is negative, this ratio to be negative, this del T has to be positive, which means temperature increases. Okay, next, if mu is equal to 0, means if this ratio is not either positive or negative but it's 0, then this implies dou T by dou P at constant enthalpy is equal to 0, which means del T is equal to 0, which implies temperature remains constant. Temperature remains same. So which means when you are throttling any fluid, depending upon this mu value, the temperature of the fluid can either increase or it can decrease, or it can remain at the same, depending upon this positive, negative, or equality to 0 of this mu value. Okay, now why this mu is really important to us? See, we'll talk a bit about it. Later, whoever faculty teaches you applied thermodynamics, he'll definitely teach you. So see here. So this is a refrigeration cycle, for example, okay, which is the conventional, vapor compression refrigeration cycle. For example, if we take 1, 2, 2, 3, 4, and the process occurs something like this, 3 to 4, you will be throttling, correct? This is, of course, condenser pressure, and this is evaporator pressure, and this is compressor, and this is throttling valve. So there will be some work input to the compressor, and fluid takes heat from this space. Correct? This is how your refrigeration cycle looks like, the conventional vapor compression refrigeration cycle. Okay, VCRS. It's called VCRS generally. Vapor compression refrigeration cycle. Okay, the name is vapor compression is given because the state of the system here is vapor, and you are compressing the vapor in a compressor. Okay, so that's why generally in Rankine cycle and all, you will be having water, fluid, liquid to compress using a pump. So generally they are not called any vapor power, vapor compression and all. But here it is called vapor compression refrigeration cycle, refrigeration system, because here the state of the fluid inside the cycle is vapor, and you will be compressing it with the help of a compressor by putting some work input to state 2. Okay, so if this is the case, this condenser pressure will be more than evaporator pressure. And generally, if you see here, we have a throttling valve. Okay, the valves that you see beside your this thing, refrigerator and all. So during throttling valve, what happens? The fluid throttles, which means its pressure drops from condenser pressure to evaporator pressure. Correct? Now, if you see, it's giving heat to the outside. So now, if you see, its temperature also has to drop during its condition. Correct? Here it is H3 and here it is H4. So now you should select a proper refrigerant such that if you have TL to TH, means some work is coming in, there is lower temperature where it is taking out some heat, and there is higher temperature to which it is rejecting heat. So which means del P or dP is negative, because of course during throttling your pressure comes from condenser pressure to evaporator pressure. Next, what about dt? Temperature should also come down, correct? Because again, if the temperature is low, only in that case the heat can take the heat with the help of this compressor. If this temperature is already high here, then heat will flow reverse into the refrigerated space. So the main thing that you need to do here is to maintain the low temperature of the refrigerant. Otherwise, what happens? Heat from the refrigerant will flow into the refrigerated space. Actually, to avoid that, we'll make this at a lower temperature, which means the fluid which is at high temperature here, generally of heat ejection, this fluid which is here, means basically fluid in the sense here refrigerant itself is the fluid. So refrigerant is the working fluid. So if you have this refrigerant as the fluid, then see what happens. Whenever this refrigerant is dropping its pressure during its throttling, look, during throttling, whenever this refrigerant is dropping its pressure, definitely the temperature also should come down, which means del T is also should be negative, which means, and during throttling enthalpy remains constant. So what should be this ratio? Greater than 0, correct? Yeah, refrigerant is connected to refrigerant is converted to, yes, refrigerant is converted to vapor, because the refrigerant will take the heat from the fridge. See, actually, if you see, this is your refrigerated space, and your refrigerant takes heat out of this and gets vaporized. Okay, refrigerant will be in liquid state here, and it comes to vapor state. And when it passes through like this, it takes out the heat from this refrigerated space. This is where you will be putting all your items. For example, milk and all. If you put here, then whatever the heat that is available in this refrigerated space, and also when temperature gets changed, hot airs move up. So that's why if you see, your deep freezer is always on the top of the fridge, because during convection, what happens? If the air is heated, then density of the heated air will be less when compared, correct? Density of cold air will be more when compared to density of hot air, which is known to us, correct? Because P is equal to O R T. Complete chamber is maintained at constant pressure. So if O is more, temperature will be low. So which means for cold air, density is high. So if you see this, if this is your milk and all, then what happens? This is your refrigerant. When it's passing, it will take the heat from this cooling chamber. And you know, when it is in liquid state, I mean, it's in somewhat wet region here, it gets vaporized by the time it takes total heat. Of course, this is a conventional cycle. So, I mean, you know, we have taken for analysis purpose. So this is how we assume the things. And now this vapor which is here is compressed with the help of a compressor that runs at the back of your fridge. You will see there is a small motor making the sound. This is the compressor that what, you know, it will compress your vapor refrigerant and send it to the superheated state by adding some more energy to it. Okay, so for refrigerant, we should have del P by del T of H greater than 0. Now, which means this mu Joule-Thomson coefficient, mu JT, for example, has to be positive. Okay, so if this is negative, what happens? When you are throttling the fluid, temperature of the fluid increases. Correct? If temperature of the fluid increases, then what happens? Heat will flow. Instead of refrigerant taking the heat from the system, what happens? Heat will flow in a reverse direction, because you know heat can always occur between 2 points of temperature change. So undoubtedly your refrigerator stops working. Okay, means there is no effect of refrigeration basically if you commit these kind of things. So when choosing a refrigerant, this ratio mu Zt, which is dou P by dou H dou P by dou T at constant enthalpy, it was a really useful thing. Okay, so see here, did you all understand what's the importance of mu Zt? Please tell me, did you all understand what's the importance of this mu Zt? Because it's very important for us to make a proper choice of the refrigerant, because a fluid we have seen, sorry, this is dou T by dou P, my friends, it's not dou P by dou T, please correct that. Okay, this is dou T by dou P, because Joule-Thomson coefficient we are defining it as dou T by dou P. Okay, it's not dou P by dou T, it's dou T by dou P. Okay, please correct that. Okay, so did you all understand why this Joule-Thomson coefficient is very important in making the refrigeration system? Because the choice of proper refrigerant depends upon this mu value. Okay, clear to all of you? So can I move ahead? For ideal gas, we'll see Joule-Thomson coefficient is not yet finished. I just show you why this mu Zt is a really important term in our engineering thermodynamics. Okay, we'll see for ideal gas what is the mu Zt and all. Okay, clear till now, till this moment? To all of you, please respond. Okay, so now we'll see what's the values for ideal gas and all. So for any fluid, the Tp means the temperature pressure curve looks like, if this is T and if this is P, so there comes a curve something like this, where this ratio will be positive, because if you draw a slope it is negative here, so mu Zt is less than 0 and mu Zt is greater than 0. Because you can see, if you remember a bit of basic calculus in your schooling, you can tell one thing: if a curve is increasing, definitely its dy by dx is positive. Correct? And since this is a constant enthalpy process, for example, H is equal to constant is the process here. So see, if H is equal to constant on a Tp curve, this is how the throttling process looks like. So there comes a point where your mu Zt will be 0. Means generally there comes a region where your Joule-Thomson coefficient is less than 0, and there will be a region where your Joule-Thomson coefficient is more than 0. But so since it's a continuous curve, there should come a point where mu Zt is equal to 0. And since you see the curve is decreasing, means as pressure is increasing, the temperature is falling. And here on the other case, as temperature is increasing, as pressure is increasing, temperature is also increasing, which means if pressure decreases, temperature also decreases. So there comes a region which is mu Zt is equal to positive. Okay, let me not do anything. Let us retain this curve like this. Okay, and this is point of inflection as well. So see here. So if you draw number of this is H is equal to constant. So if you draw different curves for same fluid, So for any given fluid, by throttling at different enthalpies, different constant enthalpies, see what happens. T, P. Okay, now if you draw first point of inflection, first H is equal to constant 1. Next, if you draw one more, let me try to draw. You will be getting something like this. H2 is equal to constant, and for one more you will be getting something like this. H3 is equal to constant, which means if you identify all the points where this mu Zt is 0, so normally these points, let me erase this and let me draw something bigger. Temperature and pressure. So now if you see, normally if you identify all the point of inversions, see, this is called inversion point because the nature of the fluid gets inverted at this point, inversion point. Okay, because if you see till this moment the mu Zt value is greater than 0, and to the right of this the mu Zt is less than 0. So this is the point where the nature of the fluid is getting inverted. Means till this point, if pressure decreases, temperature increases. If pressure and temperature both decrease or increase alone, but if you come to the right hand side of this region, means if you separate this graph into two regions, something like this, the region left of this yellow line is mu Zt greater than 0, and the region to the right is mu Zt less than 0, which means in this region if pressure increases, temperature also increases. But in this region, on the right hand side region, if pressure increases, your temperature is decreasing, which means, I'm sorry, extremely, just a second. Sorry for the phone disturbance. So see here. So what do we have now? If you shift to the right side of this curve, mu Zt, then what happens? This, as pressure increases, temperature decreases, which means the nature is inverse when compared to here. Here, along with pressure, temperature is also increasing. But to the right of the region, as pressure is increasing, your temperature is coming down. So if you draw all these curves at different enthalpies, like H1 is equal to constant, H2 is equal to constant, H3 is equal to constant and all, you will be forming a curve which will pass through these points of inversion, and this curve is called inversion curve. And basically this is the locus means the set of points which satisfy a given condition. So inversion curve is the locus of all the points where mu Zt is equal to 0. So on this curve, if you see, to the left of this curve we have mu Zt as positive, and on the right of this curve we have mu Zt negative, and this is the locus of all the points where you will be getting mu Zt is equal to 0. So similarly you can draw some other curves. Maybe H4 is equal to constant and all, different temperatures. But at every point, on every curve, we have a point such that where the fluid changes its nature when it's throttled, means in terms of its temperature and pressure. So if you see, there comes a region to the left where mu Zt is greater than 0, and there comes a region to the right where mu Zt is less than 0. Now, for refrigerants, we thought that mu Zt has to be positive, means during pressure drop, our temperature also should drop. So we should choose a refrigerant which is lying in this region. Okay, which is mu Zt greater than 0, of course. Clear to all of you why this inversion curve is important? Because if you take any fluid, if you want to throttle, depending upon the application that you are in need with, you need to select a fluid either in left region or right region. Generally for refrigerants, we go for this left region. Outer means the area which is inside this inversion curve. Okay, and this temperature generally is called, if you call this as T star, for example, this T star is called maximum inversion temperature. Means where the inversion curve meets the temperature axis. Maximum inversion temperature. Maximum inversion temperature. Okay, so this is what we have here. So did you all understand everything about this inversion properties and how the properties gets inverted here? Clear to all of you? So practically, if you know, for one process, this is the curve. So if you repeat this process for different enthalpies at different throttling stages, so then for H1, H2, H3 and all, we have different locations like this. So there is one point of mu jet is equal to 0 at every location. So the locus of all these points is called inverted curve, because the nature of the fluid to the left of the curve is something different from its right hand side. Okay. So now we'll see what is the situation for ideal gas. Okay. Okay, Vamsi, Arvind, Vijay and all of you. So see here, we'll see. In yesterday's class, I told you for any fluid, generally when enthalpy is function of temperature and pressure, we derived the expression dH is equal to Cp dt plus V minus dou V by dou T at P, dou V by dou T into T dP. Correct? This is what we got, I guess. Yes or no? Is this the expression for enthalpy that we derived yesterday? That we dealt in common? Let me see once. So Cp dt plus V minus T into dou V by dou T at P into dP. Okay, same expression we have written. V minus this thing. Okay, so V minus dou V by dou T at P into T into dP. Correct? Now, if you have ideal gas, for ideal gas, see what happens. For ideal gas, during throttling, what about dH? Please tell me, during throttling of an ideal gas, what happens to the enthalpy of the fluid? This change in enthalpy is during throttling of an ideal gas in a small devices. What happens? This value is 0. Correct? We have seen, yes, H is constant, so dH is 0. Okay, Arvind? So enthalpy remains constant, so dH value is 0. So if this is the case, this implies 0 is equal to Cp dt plus V minus dou V by dou T at constant pressure into T into dP. So if you write dt by dP value, of course, since this process is a constant enthalpy, because we have already equated this dH to 0, so dt by dP at constant is equal to, so see here, inversion of this, so T into dou V by dou T at P minus V divided by Cp. This is what we have, correct, for ideal gas. Yes or no? Just simple mathematical simplification. If you bring this term to the left hand side and if you write dt by dP, then you have this value. So this implies d mu jt, Joule Thomson coefficient, is equal to dou T by dou P at H is equal to constant, is equal to what do we have? T into dou V by dou T minus at constant pressure minus V divided by Cp. So see here. So if you apply ideal gas assumption now, we have PV is equal to RT. Correct? So at constant pressure, what is the value of dou V by dou T? At constant pressure, the value of this dou V by dou T is P into dou V by dou T is equal to R. And this implies dou V by dou T at constant pressure is equal to R by P for ideal gas, correct? Which we have also derived yesterday. So dou V by dou T at constant pressure for ideal gas is R by P. So let us substitute this expression here. So this implies mu Jt of ideal gas. Mu Jt of ideal gas is equal to, see, T into R by P, because this value for ideal gas we have got it as R by P minus V divided by Cp. So now see carefully, for ideal gas, if PV is equal to RT, what's the value of RT divided by P? All of you, please tell me, for ideal gas, if PV is equal to RT, then what's the value of RT divided by P? Please tell me, all of you. For an ideal gas, V, correct? So V minus V is 0 because this value is V. So this implies mu Jt of ideal gas is 0, which means during throttling of an ideal gas, so generally we don't have any ideal gases, but at high temperatures and reduced pressures, we can assume ideal gas behavior. We have seen that reduced properties on compressibility chart in chapter 2. So if you see, mu Jt of an ideal gas is 0, which means if you are throttling the substance, this value dou T by dou P at constant is equal to 0 for ideal gas, which means for a finite change in pressure drop, what is this change in dou T? 0, and that's why during throttling of an ideal gas, we see initial and final temperatures same. Okay, which we also used in applications of steady flow energy equations there, if you remember. Correct? Did we use that? I told you during throttling temperature doesn't change. Correct? Initial and final temperatures remains the same. Yes or no? Did we talk about this or not? Study applications of steady flow energy equations. Correct? There we have discussed something called throttling, and I told you this, if you remember. Correct? So we have seen Joule-Thomson coefficient of ideal gas is 0, and this question was asked in GATE 2020 also, which one of our friends is telling. Okay. So for ideal gas, we have this mu Jt of an ideal gas is 0. Clear to all of you? For real gases, it can be positive or less than 0, depending upon the nature, whether the gas conditions are lying to the left of the inversion curve or to the right of the inversion curve. Okay. So with this, I would like to conclude this chapter, thermodynamic relations, basically. Okay. So I hope things are fine now. We'll solve some problems on all these things which appeared in GATE in some years, and then we'll end up this course. Okay. So we'll solve some problems now. So in properties of pure substances also, we didn't solve the problem. So I put both these things in single heading, properties of pure substances. So please tell me, the relationship dou T by dou P at H is equal to 0 holds good for both A and D are correct in this case, correct? So both A and D, because we have just seen for ideal gas at any state, this dou T by dou P at constant enthalpy is 0, and also for any gas at its inversion point, the dou T by dou P at H is 0, correct? So both A and D. It was in GATE 1993, so long back. Okay. So we know mu Jt is equal to Joule-Thomson coefficient is equal to dou T by dou P at constant enthalpy, and which is equal to 0 for ideal gas. And also at its inversion point, it is 0. Next, simple definitions that we learned. During the phase change of a pure substance, Gibbs energy G is equal to H minus Ts. We solved this, correct? You remember? I defined you what is Gibbs free energy. So Gibbs function basically G is equal to H minus Ts. So Gibbs energy, dg is equal to dh minus tds minus sdt, and this dh minus tds can be written as tds is equal to dh minus vdp. So this is v. Okay, let me write this. So v dp minus s dt, and during a phase change, both pressure and temperature, remains constant. So if you see, pressure remains constant, and also Gibbs free energy is also 0. Okay, because it's given pure substance. So this pressure remains constant, temperature remains constant. So this dg is also 0. Because during a phase change, pressure and temperature they generally remains constant. Okay. So next, at a table point of a pure substance, the number of degrees of freedom is dash. So at table point, if you apply Gibbs phase rule, F is equal to C minus P plus 2. At table point, for one component, how many phases we have? It's given table point, so 3 phases plus 2. The answer is 0. Correct? 0, which we already discussed during our discussion on properties of pure substances. So F is equal to 0 at triple phase. And for water, what are the values I gave you? For water, at a triple state, for water at triple state, T is equal to 0.01 degrees centigrade and P is equal to 612 pascals. This is what the values I gave you. Correct? 0.01 degrees centigrade and P is equal to 612 pascals. Correct? We talked about all these things. So yourself, now you yourself are answering all these questions. See, Vamsi, Vijay, Arvind and all. Okay, so these are all things we have already discussed during our discussion in lecture. So all these are also previous gate questions. So see here. Now there is a fourth question. A vessel of volume 1 meter cube. A vessel of volume 1 meter cube contains a mixture of liquid water and steam in equilibrium at 1 bar. Correct? So there is one vessel of volume 1 meter cube. This volume, total volume is 1 meter cube. Next, contains a mixture of liquid water and steam in equilibrium. Okay, so there is some liquid water and steam as well. Okay, and we have steam. So given that volume of steam is 90%, means 90% of the volume is occupied by the steam. So it's given 90% of the volume is occupied by steam. So this diagram appears a bit incorrect because more volume we need to cover it with steam. Okay, so more volume let us cover with steam for the time being because it's given. So if you have things like this, then there is steam and then there is liquid water. Correct? We have this. Now, given that 90% of the volume is occupied by the steam, so volume of steam means volume occupied by steam is equal to 0.9 into 1 meter cube, so which is 0.9 meter cube per kg. I mean, sorry, not per kg. This is meter cube, just the total volume that is occupied by steam. Next, if total volume is 1 meter cube and if the volume occupied by steam is 0.9 meter cube, then what is volume occupied by liquid? Total volume is 1. Out of this 1 meter cube volume, 0.9 meter cube of volume is occupied by this steam. So 0.9 into 1 is 0.9 meter cube. If this is the case, please tell me what's the volume occupied by liquid water then? See, total is 1 meter cube, correct? So 0.1 meter cube, which is in bracket 1 minus 0.9. Okay. Okay, again you may feel this as multiplication. So let me write the things here. So 1 minus 0.9, which is equal to 0.1 meter cube. Okay, so now at this state they have given the dryness fraction of the mixture is dash. Okay, they are asking for the dryness fraction. Assume that at 1 bar, which is at this equilibrium of this tank, Vf is 0.001 and Vg is 1.7. So if you see, generally also I told you Vg will be very much higher than Vf. So if you see, this is 1.7 and this is 0.001. Okay, so practically also this Vg will be very much, which is very much greater than this V. So if you write the things, mass of liquid is equal to total volume of liquid divided by specific volume of liquid. Correct? So this is total volume of liquid is 0.9 0.1, and specific volume of the liquid is VF 0.001. So if you see, if you compare this, how much is this total? This is 10 power minus 1 divided by 10 power minus 3. So the total answer is 100, correct? 10 square, 100 kgs. Next, what is mass of steam here? Volume of steam divided by specific volume of steam, and Vg, of course, vapor, because it's given the two phases are in equilibrium, which means the value is something less. So if you see, V steam is how much at the state of 1 bar? Total volume occupied by steam is 0.9, and this value is 1.7. 0.9 divided by 1.7. Answer should be something near to 0.53 something. Please calculate. Let us calculate the things using a calculator. Let us calculate all these things using a calculator now. So see here, 0.9 divided by 1.7. This is what you have, 0.529. Okay, so 0.529. So let us store this value for some time, because we have some use of that. So see, 0.529 kg. Correct? This is 100 kg of liquid, and there is 0.529 kg of water, steam within this. So 0.9 is the total volume of the steam divided by specific volume is this, and mass of liquid is this. So now what about Dyna's fraction? X is equal to, Dyna's fraction is equal to mass of vapor divided by total mass. Correct? This is what we have. So mass of vapor divided by total mass. So now if you see the things carefully, the mass of vapor, we already stored the value 0.529, correct? So 0.529 we already stored. So this should be divided with mass of steam plus mass of water, and water mass is how much? 100 kgs. So if you see, this is the value, and 0.00526, which is 5.26 into 10 power minus 3. 5.26 into 10 power minus 3. 5.26 into 10 power minus 3 is the dryness fraction of this fluid. Okay. Yeah, 0.00526 is same as 5.26 into 10 power minus 3. So X dryness fraction is equal to 0.00526. Okay. So this is the dryness fraction of this fluid at this corresponding states. Clear? So we'll go for the next question. Okay, is there any doubt in this? Nothing, simple calculations, correct? But we know that specific volume of the liquid phase is very much less than the specific volume of the gaseous phase. If you see, this value is 1.7 and this value is 0.001, which is very small when compared to this 1.7. Okay. Next, we have one more question. In the vicinity of the table point, vicinity means nearness, correct? In the vicinity of the table point, the vapor pressures of liquid and solid ammonia are respectively given by these values. Means this is the relation to identify solid phase properties. Means if ammonia is in solid state, if you know its pressure, you can calculate its temperature using this relation. Similarly, if you know its temperature, you can calculate pressure as well. And of course, if it's in liquid phase, then this is the equation. So now, if where P is in atmospheric pressures and T is in the Kelvin, the table point temperature is dash. So the table point temperature is what he is asking for. So tell me one thing, during table point, will all the three phases coexist together? Yes or no? During the table phase of the fluid, please tell me, can these two liquid and solid phases coexist together? Yes or no? Means if the solid phase at table point is at a particular pressure and temperature, then the liquid phase is also at the same pressure and temperature, because at a table point the properties are fixed. So if you see, whatever the pressure and temperature are the properties of this liquid ammonia, same are the properties of this solid ammonia as well, correct? Which means if P and T in both these equations are same, can we equate the right hand side of these two equations? Yes or no? Please tell me. If they are at same properties, then can you please tell me this right hand sides of both these equations can be equated or not? They can be equated, yes or no? Can we equate them? Yes, we can equate them. So if you equate them at triple phase, solid phase, solid and liquid phases, coexist together, solid and liquid phases coexist together, then if you equate the right hand sides of this 15.16 minus 3063 divided by T is equal to 18.70 minus 3754 divided by T. Correct? This is what we have. So if you shift the terms to each of the side, if you shift this 3754 to the left hand side, then 754 minus 63. 754 minus 63. 1, then 9 and 6. Correct? 691 divided by T. Yes or no? 691 divided by T is equal to 18.7 minus 15.16. 18.70 minus 15.16. So this value of T we can calculate as 691 divided by 18.70 minus 15.16. Now what are the units? It's given T is in Kelvin. Okay, so this is also in Kelvin. So T is equal to, what is the value that you want? 195.19, all of you. So let me check once. 195.19. 691 divided by 691. So see here, 691 divided by 18 point, how much is the value? 18.70 minus 15.16. So 18.691 divided by 18.50 minus 18.570 minus 15.16. 691 divided by 18.70 minus 15.16. 15.16. So this is the value, which is 195.197. 195.197. 195.197 Kelvin. This is the triple point temperature of ammonia in Kelvin here. Okay. So see, I am doing all these things calculations now because you see I am typing 28 in place of 18 and all these things. So in exam you should be careful of all these things. Okay. We shouldn't make calculation mistakes. Next. Constant pressure lines in the superheated region of the Mollier diagram. Okay. This question was asked in 1995. Okay. We'll see what is this Mollier diagram. Mollier diagram. Mollier diagram is generally the one on which enthalpy and entropy are plotted, because enthalpy tells us what's the energy content within the fluid or possessed by the fluid generally, and entropy tells us what's the irreversibleness, or if entropy is more, the disorderness of the system is more. So these two are important properties, and generally there is one person named Mollier who gave this chart, which is Mollier chart, HS. And then this looks something like this. We have different Danish fractions lines on the Mollier chart. For example, if this is HS, then x is equal to 0.1, x is equal to 0.2, and x is equal to 0.3, and all these things. This goes on. Finally, we have x is equal to 1 as well. So inside this, if you want to draw constant pressure lines, for example, if you take any process at random, this is Mollier diagram actually, the Danish fractions and all we have. Mollier diagram. So if you see at a particular state, if you consider this thing, so if you want to draw a constant pressure process inside this, generally it looks something like this. Something like this with positive slope actually, and also without the knowledge of all these things also you can answer the things. See here, The only thing you should know is the Euler chart gives the relation is plotted between H and S. If you know this, this question is completed. Okay, Euler chart is something that you plot for enthalpy and entropy. So if you are plotting this, the constant pressure lines in the superheated region means somewhere here when X is more than 1 of the Euler diagram will have. So if you write TDS equations, TDS is equal to DH minus VDP. Now this is the second TDS equation, which is a basic equation to all of us. So now it's given the line is constant pressure line. If pressure is constant, this dP is 0 in the superheated region, correct? So which means T is equal to dH by ds. And now if you see the slope of any curve on a HS diagram is nothing but dH divided by ds. Euler diagram is what? That gives the direct relation between enthalpy and entropy of the fluid, and it's plotted between enthalpy and entropy axis for different dryness fractions. Okay, now if I know what's the dryness fraction and entropy, I can get what's the, for example, if dryness fraction is 0.2 and if I calculate entropy, then I can tell what's the enthalpy of the fluid by looking here. Okay, so this is how we can do it. So Euler chart is plotted between enthalpy and entropy axis. So if you know this, TDS is equal to dH minus VDP is what we have, and T is equal to dH divided by ds, because for a constant pressure line, this change in pressure dP is 0, because here P is constant. P is constant. It's given already, constant pressure lines. So now this value, we know this T is absolute temperature, what we use here. Then please tell me what could be this value. Can this T can be negative or 0? Absolute temperatures, absolute 0 and all. Tell me what could be this value, dH by ds value. Can it be positive, negative or 0? Please tell me. It's always positive, because this absolute temperature is always positive. So dH by ds is positive, which means you can see the line always have a positive slope. Means you can't have any line or this any process, constant pressure process with a negative slope like this. This is wrong. Okay, because slope can't be negative. Always it can be positive. Okay, like this. It's increasing slope normally. Clear to all of you? The only thing you should know is this Euler chart is plotted between enthalpy and entropy axis always. So superheated region is something where X is far more than 1. Clear to all of you? Okay. Are you all okay with this question? Can I go for the next question? Please respond. Yes or no? Okay. So I'm going for the next question. Which combination of the following statements is correct? Okay. A gas cools upon expansion only when its Joule-Thomson coefficient is positive in the temperature range of expansion. During expansion. So see here. Joule-Thomson coefficient. Just now we learnt about this. Correct? What's the formula for mu Jt? Dou T by dou P at H. At constant enthalpy. Correct? Now see. The gas cools upon expansion only when its Joule-Thomson coefficient is positive. Suppose if this is greater than 0, now you know during expansion what happens to the pressure? Means if volume is increasing, generally what happens to the pressure of the system, of the gas? 7th question missing. Okay, no problem. Don't forget. Don't take consideration into these numbers. We have something. Okay, so what happens to the pressure when volume is increases? Generally, when expansion is taking place, what happens to the pressure? It generally comes down. Correct? So which means if this is negative, this dou T has also be negative, because the ratio has to be maintained positive, which is given here. Joule-Thomson coefficient is positive. Means if mu Jt has to be positive, if pressure decreases, then definitely temperature also decreases. So temperature decreases, which means gas cools. Means first statement is correct. This statement is correct. Second question, second statement. For a system undergoing a process, its entropy remains constant only when the process is reversible. Means basically he is telling entropy remains constant, means the process is isentropic only if the process is reversible. Is this correct? Please tell me, is option Q correct? For the process to be isentropic, is it mandatory that the process has to be reversible? Did we see something on this statement? No. Correct? Means I told you clearly, for a process to be isentropic, process need not be irreversible. Yes? Okay. So if you see, this statement is wrong. Okay. Because I told you ds is equal to integral del q by t plus s generation for any irreversible process. So if there is some irreversible heat loss from the system, this del q term is negative, and if the magnitudes are in such a way that this s generation is actually equal to the entropy loss due to this heat ejection from the system, then this entropy still remains constant. I told you, so for any process, this entropy can increase, decrease, or it can be constant. Okay? So this statement is wrong. Next, third, the work done by a closed system in an adiabatic process is a point function. So please tell me, is this correct? The work done by a closed system in a adiabatic process is a point function. Yes or no? Not yes. Correct? Because normally work done is a path function. But in case of adiabatic process, what happens? See here. In case of adiabatic process, del q minus del w is equal to du, and in case of adiabatic process, this del q is 0, which means this del w is equal to minus du. And you know, this internal energy is a point function. If this is a point function, then definitely in this case, this value can be identified if the initial and final points are known. Because if initial and final points are known, you can calculate this change in internal energy, which is same as this work transfer. So adiabatic process is the only process where work can be treated as a work interaction, or work done by the system can be treated as a point functions. Understood? Because this work interaction is same as the change in internal energy. Clear to all of you? For adiabatic. For adiabatic process. Yes? Correct? So for adiabatic process, if you see, this del w is equal to minus du, so this is a point function, so this can also be treated as a point function for this adiabatic process. So this is correct. Next, yes, a liquid expands upon freezing when the slope of its fusion curve on pressure temperature diagram is negative. A liquid expands upon freezing when the slope of its fusion curve on pressure temperature diagram is negative. See, it's given pressure temperature means dou p by dou t or dp by dt during fusion, means for a solid this is given negative, less than 0. I'm sorry, see here. So a liquid expands upon freezing when the slope of its fusion curve on pressure temperature diagram is negative. So it's given pressure temperature diagram is negative. So what happens to the volume? This is the question of the day. So now if you see this dp by dt at fusion, if you apply this for dp by dt at saturation is equal to hfg, or you can write, maybe this can be applied at any two phase changes, like it can be this, you know, Maxwell equations are derived from basic equations like TdS equations and, you know, other Gibbs energy and Helmholtz functions, which can be applied anywhere. So I have shown you the relation when you apply this in liquid vapor region. Similarly, you can apply at fusion curve also at solid liquid regions. Correct? Does values change? No. Correct? Because Maxwell equations we have derived from the basic TdS equations, which are applicable to any of the system. Correct? So if you apply Maxwell equation at fusion point, you also have at fusion state is equal to hfg. There we call this as latent heat, L, latent heat of fusion, latent heat, let me write this neatly, latent heat of fusion divided by T of melting point temperature into volume at that particular state. So now, for example, you know, V at that particular condition, for example, V of liquid phase, we can write this. So this is what we have for a Clapeyron equation for fusion curve. Did you understand how we can write this equation? Because this equation was basically derived from Maxwell equation, and Maxwell equations are the equations which are derived from basic conservation energy laws like TdS equations and Gibbs function and Helmholtz functions. So if you see, this is the expression that we can write, and now it's given during its fusion, this value is less than 0. If this value is less than 0, this change V liquid minus V solid, Vg minus Vf type basically. So V liquid phase minus V solid phase. So if you see, if this is less than 0, latent heat of fusion is never 0 because we need to supply some heat. T melting point is also never zeros. I mean, like, it's not negative generally if you deal with absolute scale of temperatures. So what should happen? V liquid minus V solid has to be definitely less than 0, which means V liquid has to be less than V solid in this case, if you apply this Maxwell equation at the fusion phase change. So if you see, V liquid is less than V solid, which means a liquid expands upon phasing. On phasing means, you know, during a phasing, the substance which is in liquid phase will get converted to solid phase, which means V solid is greater than liquid, means during phasing, I mean phasing from liquid to solid state, the volume is increasing, which means, Vamsi, look here, if we have a curve yx, if I ask you slope, will you tell dx by dy or dy by dx? Please tell me. If you have a curve plotted on yx axis, then slope on this curve is dy by dx or dx by dy? Dy by dx. So similar is the case, because the Clausius Clapeyron equation, means the basic Maxwell equation we have is this, and here they told us it's pressure temperature diagram. So pressure divided by temperature. Okay, it's like yx curve, and you know, TS diagrams, PV diagrams and all, we have considered dp by dv at random. So here we'll consider for dp by dz. So please tell me, is the statement D correct in this discussion? Because you have seen volume of liquid is less than volume of solid, means when the substance is freezing, means from liquid phase to solid phase, the volume of the substance is increasing actually, which means the solid is expanding. Correct? Did you all understand this? Why the volume of solid phase is greater than volume of liquid phase? Because of this Clapeyron's equation that you can apply at fusion. Okay, so if you see, sorry for this, this is also correct. So actual answer is P, R and S, and you can add, yeah, option C is P, R and S, so which is here. Q is wrong, P, R and S is correct. Okay, so you see, first statement is correct, second is wrong, then third and fourth are correct. So did you all understand the logics behind why this four statement, I mean these three statements are correct, P, R and S? Did you all understand why this P, R and S are correct but Q is wrong? Yes or no? All of you, Vamsi, Vijay, Arvind, all of you, please tell me. So did you all understand why these first three statements are correct? I mean P, R and S are correct but Q is wrong? Okay. So we'll go for next question. What's the time, by the way? It's 11:30 already. Okay. So, okay, we'll stop the discussion here. So we have few more questions that which we'll cover in tomorrow's class, and that will be the last class of thermodynamics. I mean basic thermodynamics, of course, to you. Okay. So we'll meet tomorrow at 10 o'clock again, and we'll finish off these questions on properties of pure substances and thermodynamic relations. With that, we'll finish off this course. Okay. So yeah, that's it. Anything to say from your side? Notes I'll be providing, no issues for notes. I was busy with other things, so within 2-3 days, definitely I'll provide the notes of this properties of pure substances and this thermodynamic relations. Okay. Okay, clear? So can we end up this session now? Okay then, thank you all. Have a nice day.